After we carried out various analyses of the problem, including studies in both nature and cosmic rays, we returned to artificial synthesis to see if we could find any way in which to move further in this area. I would like to draw your attention to the following. See what the shell effect looks like in the region of tin. It is very localized, both in the number of protons and in the number of neutrons. And look at the superheavy area. The effect of the shells is inflated due to the large Coulomb field of the nucleus. Probably, if the influence of the Coulomb field was removed, or at least decreased, it would be much more localized and even more pronounced. But here it is smudged. You can clearly see this effect in the amplitude of the shell correction. The red area seems to indicate 10 megaelectron-volt, whereas in the blue area, it is 0. Here, we can also see the line of beta stability. Perhaps due to this smudging, we may have already reached superheavy elements. This is what we had in reactions with calcium-48 and actinide nuclei. This is the result of cold fusion, which did not reach the region of superheavy nuclei. And here are doubly magic nuclei, according to macromicroscopy, while others disagree, saying that it may be over here. We are now conducting experiments with these nuclei at the accelerator where we have heavy isotopes of element 118. We are on our way to this point, and we are getting closer to it. There is a lot of talk about the need to synthesize element 120, which is difficult to achieve. Again, you can only reach this nuclei if it rises. Therefore, experiments are now underway, and it is likely that the last result of this experiment with calcium-48 will be the answer to the question of whether it rises or not. This is very important because, should it rise, the macromicroscopic theories have to be revised. If we are able to prove that there is a nucleus here, the stability will fall, that is, there will be no rise of the magic nuclei. But for this, it is necessary to do a complex experiment in which the irradiation process will take us about 9 months. We have already completed half of this time, and the other half is still ahead of us. Let's discuss, can there be heavier nuclei than that of element 120? Could it be 122? Is this the last island of stability, or isn't it? A similar question always arises, and somehow it must be answered. Is there or isn't there? Yes or no? I would like to mention that even in the classic liquid drop model, we know that the divisibility parameter, which we denote as z squared over a divided by z squared over a sub crit, as we go towards x sub 0 equals 1, which is an extremely heavy nuclei, loses stability and, in the end, is simply lost because it is divided into 2 fragments. It is divided as follows: deformation, constriction, breaking of the neck, and then separation. If we could somehow delay this separation process and allow the process to go even further, then we would reach stability again in the form of a bubble. The bubble is much larger than the drop, but it is also made up of liquid. It is larger in size, with x0 equals more than 2. Its Coulomb forces immediately and sharply decline, while the surface tension remains the same. But this transition is taboo because there are no forms and there is no stability between the drop and the bubble. Despite the fact that the substance is the same, the figures do not transition from one into another. But in the nucleus, it may be an intermediate state. Roughly speaking, there may be a drop in the nucleus. In the middle of this nucleus, the density can decrease to form a semibubble, and then, as in the third graph, the density can decrease even more, and it will be like a bubble. That is, all of the substance will shift to the periphery of the structure, and there will be no substance in the middle. So this is a drop, this is a half drop, or a half bubble, as you like, and this is a bubble. This is a very important point, and you have probably deduced that if the nucleus expanded in order to slightly reduce this Coulomb repulsion, there could be heavier nuclei. Therefore, nuclei can be heavier than superheavy, if only the density can be changed. With all of this information, we can easily depict a line for beta stability. We can then indicate the stable continent, the peninsula of stability which includes uranium and transuranic elements, and we can draw our island of stability of superheavy elements. Now, let's move on. We will consider different configurations of nuclei with a normal density. In principle, one could go a little further. Here is the red zone, and this will be the part that refers to the nuclei where the atomic number is lower than 120. Let's call them normal nuclei, that is, of normal density. This is followed by atomic numbers higher than 120 with a higher density and referred to as semi-bubbles. But you can move even further. If the nucleus has the density of a bubble, where the atomic number is higher than 220, the number of protons will be around 300 and the number of neutrons will be around 700. Now it becomes necessary to answer the following question. Can a nucleus having a large atomic number or a large Coulomb field slightly change its own density? Interestingly, this semi-bubble, according to calculations, is located here, overlapping with the zone with normal nuclei. Isotope 292 of element 120 can already take on a semi-bubble shape. Looking at element 118, we have already reached isotope 294, and now we are trying to get to isotope 296, which is very close. The only problem is that we get very few of these nuclei. Therefore, a superheavy element factory is being built at which we will obtain more of these nuclei. There you could see if the density changes or not. If we have more of these nuclei, we should be able to calculate the total energy of the nucleus of element 120. Now let's do a mental experiment. Could the nucleus be like fullerene? It consists of alpha particles, Gamma spoke about this, and there are neutrons between them. For example, the nucleus, with an atomic number equal to 120, having 60 alpha particles and 60 neutrons, forms fullerene. What is its energy? Exactly the same as here. In principle, this can happen only if the nuclear forces, which we do not know, are such that they will make it possible to construct this complicated design.